Hello and welcome to our presentation of intents in Android, and to be more specific, implicit intents. And the reason why we are working with implicit intents is, as we'll understand in the presentation, implicit intent is very counterintuitive that you can detect a malware from implicit intent. So these might not be considered so rich features for developing an IDS, and for that reason, in this paper, we would like to break the myth that implicit intent is not rich enough to make an intrusion detection system, and will prove it by making intrusion detection system also. And beyond a malware classifier, it also offers a lot of good things. For example, it's a high-level features which we can understand intuitively as humans. The end-to-end deep learning configurations using these intents, and we ran around more than 40 configurations. So, of these in a very methodical manner, which we'll explain later in the paper. So, this paper also acts as a benchmark or a baseline for implicit intent service features when used with the intrusion detection system, because currently there exists no parallel which has benchmarked these features in isolation for a malware detection system. In Android, every process or every component that you run or every application that you open starts a process of its own. And for inter-process communication, Android has given this feature of intents. There are two types of intents: implicit intents and implicit intents. When a component or app component wants to call any other app component for a particular reason or a particular intent that it has, it will call an explicit intent, because it knows which app component it is calling and which particular service of that app entity it is calling. In that case, it will call the destination app calling by package name or a fully qualified class name that it. An example of such an explicit intent would be you are sharing a particular image from your gallery to WhatsApp. Now your gallery becomes your source application and the WhatsApp becomes a target application. You specifically call that. Whereas other type of intent is an implicit intent, in which you do not know on which particular application do a particular service that you want to be done. So for example, if I want to browse a particular website, I saw a link in WhatsApp, I just click that particular link in WhatsApp. So now WhatsApp doesn't know what are the browsers that I have in which particular browser. This will come into the category of implicit intent. So how implicit intents are resolved by the system is, each app that can do a particular service declares that to the Android system in the manifest.xml. So in manifest.xml, you have a list of declared implicit intents. Now, this part is very counterintuitive, because if there's a malicious app, why would it declare that it wants to do something? But in the case of implicit intent, even if it declares to the Android system that I have this capability to say browse a particular page, it will be given the option to browse a particular page only if a particular app requires a browsing feature, and even then it will come to the user that app browsing feature is required, which browser do you want it. So these features are, as we understand from here, not very intuitive to make. There are a lot of experiments and we tried more than 40 end-to-end deep learning configurations, deep learning all throughout, right from the unsupervised, supervised, or any of the stages in between, and they actually directly consume your dense cells instead of like a serialized prediction from it. These configurations are called end-to-end deep learning configuration. We try more than 40 end-to-end deep learning configurations in a very methodically manner in terms of how we define the different layer sizes and the interconnections between. The third and the most important part of the contributions is actually benchmarking a particular intrusion detection system using implicit intent features alone. Why this is important? Because implicit intents are amongst the easiest to extract features from a particular, and if you can build a powerful intrusion detection system or even a decent intrusion detection system based on these features alone, then you can actually make redundant any need for extracting very complex features. And in the case of Android, as we understand next, a lot of these features come from dynamic analysis and not from static analysis of the apps. That is why these features became a lot of importance. The second reason why it gains a lot of importance is that this can give rise to a lot of different architectures, even if and that is why we see such easy to implement, easy to extract features are very important to benchmark. And there exists nothing in the literature that benchmark implicit intents alone for even an intrusion detection system, for instance. So let's come to understanding it deeply, because we say that these are high-level features. So as compared to opcodes, so which we will not be able to understand, even API calls, which was difficult to understand by humans. So if we see over here in table 1, in table 2, These are the implicit intents for some of the malicious and non-malicious apps. Table 3, we have taken the difference of the frequencies in which these particular implicit intents are called in malicious apps versus non-malicious apps, and we have normalized that frequency. Some of the malicious apps, these are the top 10 implicit intents by difference from non-malicious. So data removed, keto connected, input methods changed. Now these are very, so a malicious app is removing the data installed, which besides capturing your keystrokes and putting them into the applications that desires them, they might also be sending it to some other places or using them for other malicious. If you see this particular list in table 3, that becomes very intuitive how malicious apps could be different from non-malicious apps in terms of what. So let's come to the related work on making an IDS for Android. So there are two types of systems basically. The static analysis and the dynamic analysis. Dynamic analysis requires sandboxing to behavior of the app, capture the API calls or the behavior. So most of the dynamic analysis cannot be fitted into an online intrusion detection system. So a lot of focus of malware detection system and intrusion detection system is on static features. So there are, though, in the case of Android, very few static features. So a lot of those comes from the API calls, which are considered dynamic. So permissions has been one thing which has very common in terms of static features, and a lot of work has been done on permissions because when the malicious, obviously you are calling for a particular permission, so maybe to use your camera, to use a microphone, to use the storage, and it's not so much work has gone inside intent as much as work has gone inside permissions. Then there are opcodes. Opcodes require disassembly. They are still a part of static features because you can just take the APK, you can extract the files from it, and you can disassemble those files. So they are, you can say, not so much easy to extract, but they are still considered static features because you can get opcodes without even executing the app. So permissions and opcodes are the primary ones that are being used in most of the work that we see, and then there comes other things which are bundled in the case of hybrid systems where API calls, and we are using a dataset which is Drebin, which is also published by the same author. So once we come to our architecture, so in architecture we have actually two components. One is the auto encoder, and the second one is multi-layer perceptron based deep neural networks. Two-end architectures, both of these things work in tandem, so you do not serialize the predictions, so you cannot treat them in isolation. So but we cannot actually just go about all the permutations of the configuration record. So we use a very methodological and practical way of doing it. And so since autoencoder first comes in the network, we'll first try to optimize the autoencoders. And to optimize the autoencoders, we will use two criteria. One is obviously the validation loss of reconstitution error that we have, which we actually apply on validation data and then see compute the loss of the autoencoder. But in many of the cases, we'll see like it is being tried because those loss will be very small numbers. So the second criteria that we have kept is we have connected a default MLP DNA at the end of the autoencoder, and we have gone with the AUC of that. So wherever is the type, the second criteria works with the type. So first we started with the number of layers and the size of each layer. So if you see table number 4, this is experiments with single layer autoencoders. We have tried the autoencoders from 32 to say 256 size number of neurons in that single layer. Why 256? Why we stop at 256? Because we have maximum intent is 273, and the purpose of autoencoder is very similar to what you would do as PCA for the other non-deep configurations, which is number 1 to make the features dense. Number 2 is to reduce the cardinality of your feature set. So, and since we have a 273 number of intents, so the maximum that we have taken is 250. From these, we find out that layers up till 128 gives very good results. After that, we do not get much of the gain. So, for the next stage, when we try for 2 layers autoencoders, we have stopped up to maximum of 128. And since every subsequent layer tries to reduce the number of neurons, or at max keep it number of same. We have for the second layer also we have not gone above 120. And we see from these experiments that a configuration of 128 and 64, which is a 2-layer autoencoder. The first layer is 128, and the second layer of 64. We are talking in terms of encoder. Obviously, decoder will take the opposite architecture, and the dimentic dimensions of 22 gives us the best results. We tried it for 3 layers as well, but none of the 3 layers could very good results. So we didn't try it beyond 3 layers. So that is how you get to the best configurations of an autoencoder, number of layers and the size of each layer. Then we actually start changing the configurations of our multiple MLP DNA, which is multi-layer perceptron deep neural network. And we follow a same sort of a combinations over there. First, we start with the number of layers and then the size of each layer in combination. And in that, we found that layer set of 4-layer multi-layer perceptron. We tried from 1 layer up to 6 layers, as you can see, and a 4-layer multi-layer perceptron, which each layer size of 64 neurons gave us the best. In terms of criteria for MLP DNA, we again have two criteria. So one is the AUC, and the second is the accuracy at a probability cutoff of 0.5. So you can actually achieve different numbers of accuracy and FPRs, both are related numbers, for different cutoffs in nature. And in any deployed applications, we would actually go to a different application or different cutoffs to see which is the most best combination of accuracy and FPR that serves the particular purpose. So in this particular case, since we do not have the end results of the application, so we have gone by the default cutoff, which is 0.5 for most of the algorithms in machine. So the primary criteria is AUC, area under the curve, which takes into account a lot of different things, so you don't have to think twice. But whenever there is a try, which will be in very few cases, we'll go by the second. If you see, there are some other statistics also of interest, which is number one, best accuracy and the best F1 measures. F1 measure is a combination of your precision and result as like a balance between equal balance. So this is also like one of the measures that is used very widely in this area. And obviously, we have the best accuracy, which is if you do not take care of the false arms, you let as many false arms come. What is the maximum? The second stage, once we have finalized the number of layers and the size of each layer, we would like to see the epochs optimizer batch size. So we tried it for different epochs. So after we tried it for 1,000, you can actually do it as much as the computational capacity you have. But we found that after some hundreds, the graphs have plateaus. There is no much increment. So we didn't try it more than 1,000. And we see that there is a slight improvement in 1,000. So for all the remaining experiments, we'll go with 1,000 epochs of thing. And then we try to see if one optimizer is better than another. And if you go to the literature of the different types of optimizers, 3 optimizers that are very prominent in terms of MLP DNA. And we found out that RMS prop gives us the best results. So we take RMS for prop power to see the batch size. The basic recommendation for batch size is increase the batch size to as much as the GPU can handle or the infrastructure can. But in this particular case, there might be slight differences also in terms of the learning and update of the gradient of the data is limited. And obviously, in the case of malware detection system, it is not enough. So how many passes you make to that data can actually overfit, and if there's very less data, then the gradient update is not solved. And then the last table shows us the complete end-to-end configuration that gave us the best. So in summary of the results and the discussion, there are very good results that are possible from implicit intent. These are very intuitive results as well. If you see what it can do as compared to other Challenger data from making an ID intelligent detection system. And once we actually get to the machine learning part of it and we use the deep learning, we found that we can make a very potent intelligent detection system out of it. We can get like an area under the curve statistics of more than 81%, which is considered very decent. Accuracy of more than 77% with an FPR of 0.1. And one of the interesting observations that we have is that we talked about 3-4 different types of performance indicators. So all the 3 were best for these particular configurations, which is double validation of the work that we have done. So in conclusion, we would like to say that implicit intents are the easiest features to extract. They are one of the most intuitive features for the humans to understand. So they are not so widely used in applications and not at all used in isolation in any of the literature so far. And we believe that given the intuitiveness that these features bring, people also, they offer very good insights in terms of making an malware detection. The second conclusion is that we experimented with these so many end-to-end deep learning configurations. That also brings in terms of another topic of how do we train these particular configurations, how do you train them in tandem, and also what is the AUC and the PRs that you bring out of it, which acts as a baseline for all the other works that is done in the future. And given that a very potent online, real-time, easy to implement, easy to track features, so based IDS could be made out of these features, we expect a lot of future works to go in this direction. So these are the references for our paper. And with this, we would like to say you thank you.